Right. So we may as well get started, and let's it's there to make it easier to see things. So now let's take this. So what is this?
Battery pack.
It's a battery pack. So let's take this out. So what's this?
Battery.
All right, that's interesting. What does battery mean?
Um, uh, Power.
So when we go into a shop, we go and call these things batteries, which is rather interesting. And
Mhm.
this one is an AA one, and you
Yeah.
can get slightly narrower ones, which are AAA, and you can also get C and D cells as well. And one of the things is that we use battery to refer to things that are not things that produce power. Where else do we use the word battery?
Um, uh, Check your battery. Check,
Sorry, yeah.
checking battery.
So another way we use the word battery is a battery hen or a
Hmm.
gun battery. And when we keep battery hens, do we just have one? No, we have lots of them. And if we have a gun battery, we don't just have one artillery piece, we have lots of them. A gun battery on a ship can have 4, 5, 6, 10, 12 guns. So battery actually means more than one. And in physics, the physicists don't call this a battery, they call this a cell because there's only one cell inside this container.
Yeah.
And if we put two cells together, we now call this a battery. Has any of you ever seen this symbol that is drawn on my plastic case containing my two cells to make up a battery? Do you recognize anything on there? Whoops, let's put it against the white background.
Um, does it mean it's just wired up in a parallel connection?
Well, this is a series connection
There
because
is, right.
one, two. I know they look as if they're parallel, but the
Yeah.
way they're wired is in series.
Okay.
So in at the top there, we have a symbol,
Mhm.
and that symbol has a minus sign there. That's the negative end of our battery, because when we look at our cell, you should see that one end will have a plus on it. So the positive end of the cell, and there's the negative end of the cell, because this produces direct current. The current doesn't change. So we've got our plus and our minus there, and we've got this symbol there. And this is the symbol for a battery. So it has a longer line, a shorter line, a longer line, and a shorter line. So the symbol for a cell is just going to be a long line and then a shorter line. Does
Yeah.
anyone know how we can make cells or batteries? Any ideas?
At the S, two metals.
Well done. So we need two metals and we need something else.
Uh, the acid liquid.
Right. Okay. So you've mentioned the acid. earlier on, we were looking at the sulfuric acid, the battery acid. So
Yeah.
if we take two pieces of lead
Mhm.
and connect them to wires and then hang them into a pot of sulfuric acid, we can
Mhm.
produce what most people would describe as a car battery. These people, the Tesla batteries are, of course, different. So the electric cars don't use traditional car batteries.
Yeah.
The car batteries that were found in milk floats, in railway carriages, and all of that, and even in modern internal combustion engine cars, are
Mhm.
all lead acid batteries.
Yeah.
And so we have those two pieces of metal, they hang into this solution.
Mhm.
And if we put electricity in, a set of chemical reactions occur, and the electricity is then stored as chemical energy in the pot.
Yeah.
But when we connect up those two contacts to a bulb or to a starter motor, we can get that chemical energy out and turn it back into electrical energy to do something like lighting a lamp, running a motor.
Yeah.
Does any of you know who discovered the first battery?
No.
So Alessandro Volta was an Italian experimental scientist, and he was working with a professor of biology, I believe, Luigi Galvini. And Luigi Galvini was dissecting a frog. And what they noticed was that when they touched the frog leg with the steel scalpel, the frog's leg moved. And Galvini thought it was interesting, but carried on with his biology, whereas Alessandro Volta decided to investigate further. And what he found out was that the frog's leg was hung on the apparatus using a different metal to the steel scalpel, and that when these two metals came into contact with the leg, they caused a current of electricity to flow, which caused the muscle to twitch, because when we move our muscles, we're sending electrical signals from our brain to our fingers, and these signals tell the muscles to contract and move my hand, for
Yeah.
instance. So Alessandro Volta started making his galvanic cells, these sort of voltaic piles. And if you go to the Royal Institution in Piccadilly in London, you will see one of Alessandro Volta's voltaic piles, named after him, of course. And these were the first sort of normal batteries and cells. And Sir Humphrey Davy and Michael Faraday, who were Sir Humphrey Davy was the first director, and Michael Faraday took over from him, used these early batteries to do some really interesting science. Sir Humphrey Davy used these batteries to extract elements, which is really important in chemistry, and that's why Sir Humphrey Davy is one of the he's discovered more elements than anybody else, and that I think 11 elements were discovered in the Royal Institution in London, of which they're immensely proud of. So we've got this cell or battery now, and Alessandro Volta's given his name to this. Now, where's it gone? There we are. On our cell here, we can see it says 1.5 V. And so this is a 1.5 volt cell.
Yeah.
And so when I connect in my, I've now should have 3 volts across between these two terminals.
Yeah.
So let's, and here we have a voltmeter, and
Yeah.
at the moment it's measuring around 0, as you would expect. Let's take our battery pack and put it on there. And as you can see, we've got, I think that's 2, isn't it? Yeah, about 2 volts, which is what I would expect, because these batteries have been misused by all sorts of students that I teach, and they're a bit discharged. Let's take this battery pack. I've got another one here. We can test this one here by connecting it across. Oh, wow, that one's giving absolutely nothing. Let's go and swap it around. Oh, these ones are almost flat. So that's rather interesting. Let's go and do another test. Do you know what this is?
Light bulb.
Yep, a light bulb or a lamp. Notice this has a symbol on it. This electronic set is quite useful because it has the symbol for our cell and battery on there. And it's got the symbol for our lamp on there. If you look in certain books, you might see a different symbol for a lamp, and that has that curly wire inside the circle. But it does depend on the science book, but really it should be the X that you should have there. And if we connect the bulb across there, and as we would expect, it shouldn't light up because those batteries appear to be dead. Well, let's go and grab this battery here, these 2 cells. And when we connect it up across, we show that our lamp there lights up.
Yeah.
So why does the lamp light up?
Because batteries are giving off energy, and the whole string inside the bulb that kind of kicks the heat and just lights up.
So why is the bulb not lit now? So it's connected. We've got our pair of cells. It's connected there. The electricity can travel up along the wires, which you can't really see, through the blue connector to this green thing here, and then back.
It's not a full circuit because you put a switch onto the cell.
Right.
Yeah.
And when I push this push switch down, the lamp will light up. So electricity must go in a circle for it to flow. So we're getting our packets of electrical charge. They're moving along the wire. When they get to the bulb, they release light as they squeeze through the wire, and then they head back round. But as soon as we break that circuit, those packets of energy moving through the wire now are stopped. They can't get over that gap. It's like a lift bridge has opened up and stopped the electricity from flowing. So there is our first circuit there. Notice they call it circuit, just like on the motor racing or horse racing circuits there. Ooh. Really? Yes. What's happened now?
Connected 2 up.
Yeah. Any other difference can we notice?
Power divides out, so each bulb gets a smaller amount.
Yeah, so these bulbs are dimmer. They aren't getting the same amount of electricity, we could say, as they had previously. They're having to share the voltage, and so they're a bit dimmer.
Mhm.
Let's do this. Oops. Oh, so that's it. What do we notice now?
Um, there's more energy in the light bulbs. There's more power.
Yeah, they've got brighter.
Mhm.
And so why have they got brighter? We've got the same amount of chemical energy being pushed out of our cells there, but we've got something odd occurring. Is that now each one of these lamps has now got the same 2 volts as we proved using this.
Mhm.
Each one has got 2 volts, and so it's brighter. Whereas with the previous circuit, the series circuit, because you get
Mhm.
one component after another,
Mhm.
is that each one has got 1.5 because each is getting 1 or half the amount of the previous there. So we can make different circuits for different uses. This one is going to be so much more useful if we say wanted to wire up a house, because we could put a switch on each of these lamps and then we can turn them on and off independently.
Yeah.
And let's so that's our parallel circuit.
Yeah.
Rather useful. Notice we now have another component there, and that is our typical switch, that lift bridge that opens up to stop the flow of electricity and
Yeah.
turn something off. So this is a pull switch that you find on various bits and pieces, and that's wired in there. So we've got our switch, we've got our voltmeter, we've got our 2 cells making up our battery,
Yeah.
and we've got our lamp. So let us take this. What is this?
It's a Tesla coil.
No.
Motor.
Yep, this is an electric motor. Tesla's work is rather interesting. Tesla was the last great experimenter with electricity, and he was able to do all sorts of things with electricity that's really important to our lives. So people like Faraday invented the electric motor, which I've just shown you here. And this electric motor, here's one that's disconnected from the plastic sets. This has come out of a children's toy, actually. And when this has electricity applied to it, you might be able to hear it. Let's see. Let's put a... You can see it spinning.
Yeah.
So all I've done there is I've sellotaped 2 cells together. I've sellotaped a paperclip on the back.
Mhm.
And when I connect the terminals like this, it causes the motor to spin. And
Yeah.
with Faraday's electric motors, there is only 2 pushes per rotation.
Mhm.
Now, Tesla was a genius. He noticed that you could get more pushes per turn. Now, I don't know where you live, but I don't know whether you go on trains very often. If you live in Kent, you might hear certain trains when they start leaving the station, they produce this hum, electric trains, and you will hear the hum changing in pitch. And what that is was to do with Tesla. And Tesla realized that electricity is flowing through the wires as a wave. And that if you sent another wave chasing it, as long as it was out of phase, so that the peaks didn't match up, you could run several phases through the wires. And that's how those electric trains are working, is that as they accelerate, they're adding another phase. So that first hum is the minimum power level, and then when that other pitch appears, that means that the second phase has gone and the train accelerates a bit more, and then third phase, fourth phase, fifth phase. If you work in some factories, the electricity is a three-phase supply. So you have 3 times as much power through the same wire, which is really useful because as we add more and more electricity to go through our wires, they get hot. And in the case of our lamp here, it will glow and produce light. Well, if we start running more and more electricity through this, it will glow, it will melt, it will catch fire. So being able to send more electricity in different phases down the wires is really important. Unfortunately, Tesla's work isn't of any relevance to GCSE, but I thought I'd talk a bit about how important Tesla is that so many of our devices have been made simpler and more useful because of Nikolai Tesla. So just like Swan and Edison and Faraday, they have helped build the modern world or provided the facilities for the modern world to run, because imagining a world without electricity would be truly horrible, because we use electricity almost all in every sort of realm of our life. So let's go and connect my electric motor up to our electric to the battery pack, and as we can see, it's spinning. How many circles can you see?
4.
Anybody else?
Yeah, 4.
Right, let's so what's going on here?
It's rotating.
How many circles are there now?
1. Oh, sorry. Yeah, 1 big circle.
None. It's a spiral.
That's a spiral, isn't it?
Yeah.
It's like a whirlpool. But when we spin it, our eyes see these circles which are really not there. And it's one of the things when we use our eyes, they take images, snapshot images, just like a camera, and it's joined into a moving image in our brain. And so if something is changing quite rapidly, we might see these stationary objects as moving objects, which is how old-fashioned cinema worked, in that you had this film strip that would move through the gates of a projector, and these still images changing every 36 frames a second. Although the home movies, sometimes you had 8 frames a second. So having this sort of this changing a different image, changing the image, which has a slight change to it, can create this moving picture, and you can produce stop motion animation. I know several students I've taught have made their own stop motion films using Lego men, where they would take a picture of a Lego scene, move a Lego man, take another picture, and then run it on a computer to show a movie.
Yeah.
A bit like Wallace and Gromit, where they changed the plasticine to get that. And that is an interesting example of optics there. So now we have seen that this electric motor is turning. And if I take the electric motor and swap it around, do we notice what's happened?
It's rotating the opposite way.
Exactly. So this electric motor, depending on how we connect it, it will depend on which way it will rotate.
Mhm.
And that is to do with a law of physics, where you have the current, the motion, and the field. So left-hand rule. So the thumb shows the motion, the first finger field, second finger current. And if we change the current around, notice the motion is now the opposite direction. And
Yeah.
this is one of the interesting things that Michael Faraday discovered, is that if you take a wire and run electricity through it, it produces a magnetic field. And if you put it anywhere near any magnet, it will interact with that magnetic field. And so in here is a coil of wire, which when electricity runs into it, it interacts with two permanent magnets in our electric motor and creates this lovely rotational motion. Because of the way it is set up. When we look at more about electric motors and these sort of magnetic electric effects, I will assemble electric motors in front of this camera, and you'll be able to see exactly how they work. I've got simple little models, and I could also send instructions to you to show you how you can make them using bits and pieces that you find around the house, or looking on eBay. You can get all sorts of little things. So these sort of electric motors can be got on eBay. Of course, you can make up a battery pack by using some sellotape and some paper clips. But of course, you can get proper battery holders that hold everything together. So we've now looked at our electric motor. What is this?
Like it kind of slows the voltage down and increases it.
Right, so this is a little control knob, and sometimes if we've got old-fashioned electronic things like radios and hi-fis, we might actually see these sort of control knobs, and you can have a low power setting and a high power setting. Well, let's look and see what this does. So here we've dimmed this control, and as we turn it, it gets brighter, dimmer, brighter, dimmer. And so we can use this for dimmer switches, which we have in certain houses. And also sometimes if you've got an electric cooker, it might actually be working by when you turn the control knob of the oven. It might have one of these behind, so making it the oven cooler or the oven hotter.
Yeah.
whoever designed this wasn't really thinking at that time, but behind there you can see the symbol for this, and it has a rectangle with an arrow going through this. This is a variable resistor, so it resists the flow of electricity. So the more it resists, the dimmer the light will get, the less it resists, the brighter the lamp will get. So this steals the electricity out of the circuit, making the bulb dimmer, or if it's set to its lowest setting, it will allow most of it to go through and not steal anything, or only a tiny amount. So that's our next component. Oh yes, we missed the other one. Where's it gone? Here. Yeah. Trying to find one of these that has, yeah. So there's one of the symbols for motors there, a circle with these two little blocks on the edge. For the IGCSE, they want you to have a circle with an M in it. Interestingly, this one doesn't have its M on there, which is rather disappointing. And this one is very similar, and it doesn't have the M on there, but the circle with the M in it is referring to an electric motor.
Yep.
So let's go and look at another piece of Does anyone know what these are?
Resistors. Sorry, no, light bulbs.
So they look like light bulbs. Well, let's go and do some testing with them here. So let's make up our circuit. Let's put this onto there. Whoops. And so there's our circuit there. And if we turn it on, nothing happens. It's always nice that experiments to do with electricity actually work. If you went to a school and saw someone, a teacher doing this, you would see occasionally it wouldn't work. But I knew that this was not going to work. And the reason why I knew this wasn't going to work is, can you see that there's a plus on the battery pack?
Yeah.
And can you see on this new component, notice where the plus is? It's on the wrong side. So this component is different from the previous ones. Our lamp here does not care whether it's that way round or this way round.
Yeah.
The electricity runs through the lamp and gives off light quite happily, and it doesn't care. Now, our voltmeter also has a plus on it, but in a lot of ways it shouldn't actually care which way round it goes.
Yeah.
Our variable resistor doesn't have a plus because it's just acting as a resistor. It doesn't matter which way round it is.
Yeah.
Now, of course, our electric motor does care which way round it is, because if we want it to turn in a clockwise direction, we need to make sure it's around one way. And if we want it to go in an anti-clockwise direction, we need to have it going around the other way.
Yeah.
But this component is different. Is when it is round the correct way, it lights up. But when it's around the other way, it doesn't. Now, the other interesting thing about this component is, let's grab another one of them. Let's go and put them together. Then let's grab our power supply there. Have I connected the right way round? No. Connect it this way round. For September, I'm going to get another web camera and we can have that sitting, looking down on these circuits rather than me holding them up, which is going to be so much better. And let's turn this on. And nothing's happening. So there's another difference with this component. Well, let's go and modify my circuit with some connectors here and see what happens. Let's make sure I get it the same way around. So these components do not work in series. If you put them in a row, they won't light up. So if you used them in a Christmas tree light circuit, it wouldn't work. And these are very common now, being used in all sorts of things. These are LEDs. Does anyone know where we use LEDs now?
Light bulb.
Yes, so we can have LED lights in our house. And if you go and look into the bulb, if it's a clear lamp fitting, you can see the different LEDs there. There's usually more than one in there. Sometimes you'll see 4 yellow things in there that glow. When you look at traffic lights now, most of those are now LEDs. There's not one lamp behind there. There's a whole set of little small LEDs. The signals on the railways, you'll see that there's these little small little lamps which are LEDs. Car headlamps, a lot of those are LEDs. So LEDs are really quite common now because they don't rely on very much electricity to work. They're not using the 1 volt or 2 volts that the power supply is giving them. They have this little component on the back. Here's a resistor, because the LEDs use less power, so your LED torch will last for a lot longer. And the resistor there prevents too much power going through the LED, which will cause it to break. So these are LEDs. Does anyone know what LED stands for?
Light emitting diode.
Yep. So LED stands for light emitting diode, and a diode is a special component that only allows electricity to go one way. Let's see if I can find an actual diode. That is a diode there. And so it's like a one-way street in our circuit. So it only allows the electricity to go from where my finger is to the other side. It can't go backwards. So this can be quite useful to make electricity go the right direction, and it will cause these things not to light up if they're going the wrong direction. So we've got our diode there that is acting as a one-way street. The LEDs just give off light as they're doing their job. So we have our diode, our light emitting diode, our voltmeter, our motor, our variable resistor. We talked about resistors there. Unfortunately, this set has been made by someone who's been very naughty. This is the older symbol for a resistor. In the GCSE, they're just using the symbol of a box, a bit like that box there with the arrow through. If you take the arrow off and just have a box there, that oblong or rectangle denotes a resistor. So in certain books, you'll notice that there are sometimes multiple symbols to code things in these circuits, and it's rather unfortunate, but you're supposed to use the box. But I'll give you a sheet that will show all of the different circuit symbols that you need to know, and how they're wired up. Now let's go and look at another device, and let's go and take that one. Gonna be that one. Does anyone know what this is?
Speaker.
Right, that's interesting. So here is a speaker. There's its symbol, and you can see the back of it. You might have seen inside a hi-fi. You can see this base, and you can see the black cone hiding in there, held in that metal frame, and the two connectors. So this is a speaker, but this other thing is a bit different.
Yeah.
Let's see. This is a siren.
Okay.
And once again, it's got our color-coded wires. So when I connect the black wire onto one end of our battery pack here, let's make sure I'm holding it there, and the red wire on there. Notice it's now not playing. So now if I take that positive end there and put the red onto the positive end and the black onto the negative end, it plays. So this is another component that does not like to be connected around the wrong way, and that's why we've got this color coding of the wires. The red is denoting the live, the black is denoting the negative.
Yeah.
So there's another component, our buzzer or bell. Some of them have a bell inside there. And here's another one here, a different type. And that's it. Oh, is it not? Oh, it's not working. Why is it not working? Oh, first component that doesn't seem to want to work. Let's see if I can find another one. Let's grab this one. Plus. There we are. Where have you heard that sound before? These are those smoke alarm buzzers, sirens, and so that can be used there. But there are all sorts of different designs. So this is the sort of smoke alarm, fire alarm one. Here we have our siren. There's this one here, which is another different one. So another one showing that siren there as well. So let's go and look to see what other ones we have got here. We saw the LEDs that were red. Here are a yellow one and a green one. So we can produce multiple colors, a bit like in a traffic light. Let's try and get that connected up. Let's connect it up the correct way. And there is our ones there. And if I connect it around the right way, whoop. So we can get multiple colors, just like with our lamps. Although usually the lamps, they color the glass lamp bulb there to give the different colors, or they have some sort of lens that will give the different colors. So there's our LEDs there. Let's go and look at this. Here's another component here. And let's see. And this is another type of switch. Let's see. Now let's get it set up. Let's put that there. And that there. And let's find this. Whoop. Now. So how's this working?
I'm not sure.
It's almost magical, isn't it? I just move this red speaker next to the green and it will cause it to light up. In the back of our speaker here is a magnet, and this is a magnetic switch. It's a reed switch, and these are used in security circuits. Also car doors, when you open the car door, the light will go on because there's a special type of reed switch that detects that the magnet has been moved. And so when the switch is in a magnetic field, the two wires inside join together and allow electricity to flow. And when the magnetic field is moved away, and notice that it is incredibly quick at turning things on and off. So these reed switches are quite useful to use as things to turn things on and off. So there is a reasonable selection of electronic circuit symbols that we have looked at today. We haven't looked at the ammeters. My ammeters I use are multimeters that electricians use rather than being proper ammeters. And so it's a bit pointless looking at this box with a number on it, which can measure resistance, current, volts, and the various different electrical quantities, because electricity can be quite confusing in that one moment we're talking about watts. I want a 60-watt lamp or a 1 kilowatt kettle, a 3 kilowatt Hoover. So one moment we're using watts. One moment we're talking about, I need a 1.5 volt power supply. I need 12 volts, 240 volts. Then we talk about the current. a 3 amp fuse, a 13 amp fuse, a 5 amp fuse, a 1 amp fuse. Let's go and show you a fuse. There's a fuse there, and I don't think you, oh yeah, you can just see the wire that goes through there. So if too much electricity flows through there, it'll melt the wire and shut off the power, so protecting the circuit. So some of these battery holders, these cells, battery packs have these fuses there to protect the circuits. And you can use that. This one, the fuse is broken, so I've put a paper clip across there so it'll carry the power, and so the fuse no longer protects the circuit, but the circuit will work. Notice that the cells have fallen out of this. So today we have been looking at a bit about electrical circuits and the different symbols. We haven't covered all the symbols. So the physics syllabus looks at forces of motion and looks at speed, acceleration, momentum, and all of those quantities to do with the things that move around us. So that's one of the topics of the physics. Then there's the electrical section where it looks at house wiring and the various things that protect the houses. Then there's bits on electric motors and transformers. Then there's a section on energy, heat energy, and of course the different other types of energy. We've come across chemical energy. They no longer like talking about electrical energy being a store now, but people talk about electrical energy quite often. So the different types of energy. There's a section on astronomy, and there is a section on nuclear power. And finally, there's a section on density, pressure, and these other quantities. A lot of it overlaps with the chemistry. So the radioactivity section, the structure of the atom overlaps. In the energy, the calorimetry experiments are also found in the physics syllabus, in the chemistry syllabus, and there's an overlap with temperature and to some extent pressure with the chemistry. So it's quite handy if you're studying both GCSEs, is that there's one bit of information and you can be asked about it in two different exams, which is always nice to get more marks for one piece of knowledge than the other. So once again, the IGCSE sciences are very similar to the school GCSEs that they study in mainstream schools. Private schools usually study the IGCSEs. So the IGCSE Physics, we really do need to have a 2-year course. There's a bit too much to cover in 1 year. So that's 5 terms as opposed to only 3 terms and so on. So there's 2 exam papers at the end for the GCSE, and once again, the syllabus is narrow. They ask lots of questions. So in that second year, after Christmas, we'll be doing revision and doing lots and lots of past papers. There's an assignment to do after each hour lesson per week, which I will mark. And is there any other questions?
No, it's no, not really, no.
Right, good. Right. Okay. So I have managed to convey everything. I think there isn't anything else.
Thanks.
I think they've got a video of the previous trial lessons as well somewhere, and I think I explained it better in that one, but
Yeah.
it was a month ago and I can't entirely remember. But yeah, if you've got any questions, get in touch. I'm happy to answer any questions about the syllabus and what people are studying, and what they will need. There is a textbook for both the chemistry and the physics, but it's expensive and it's not very useful. I generally give out the CGP loan CGP revision books to my in-person students, but you can easily get the CGP revision guides, and they're cheap and they've got most of the information you need, so that's that should be fine. But yeah, if there isn't any questions, we can finish, I think, and perhaps see you in September.
Good, thanks.
Yeah,